This is the 16th video in a series devoted to proofwriting, and today we're going to talk about relations. So let's just jump into the definition. So a relation on a set A is merely a subset of the cross product of A with itself. And so this subset could really be anything. So in fact, the empty set is a subset of A cross A. That means the empty set is technically a relation on A. But this is not a super interesting relation. This says that nothing is related to each other. So an element isn't even related to itself. Whereas at the other end of the spectrum, A cross A is a subset of itself. And that's almost like too much. That says that everything is related. And so of course, to have meaningful relations, we probably need something in between here. That would be most interesting. And also, we'd probably like those relations to have certain conditions, and we'll introduce those conditions as we move through this video, and we'll study them more in upcoming videos. Okay, now I'd like to say a little bit about notation. So often, if an ordered pair x comma y is an element of R, then we say that x and y are related via R, and often we write x, r, y. Okay, so let's look at an example. So let's say we've got this set A, and it's the three element set A, B, C. And let's say we've got a couple of relations. So let's say we have R1, which has A comma A in it, A comma B, and then maybe A comma C and C comma A. And then let's maybe also say that we have R2, and maybe R2 is equal to A comma B, B comma C, and then maybe C comma A. Okay, nice. And so those are definitely relations, and we know they're relations because they're both subsets of the cross product of A with itself, and that's all it takes to be a relation. But that being said, let's practice with some of the notation just really quickly. So let's take this R1 and make the following observation. So notice that A is related to itself via R1, so A R1A, and that's because A comma A is an element of R1. Whereas B is not related to A via R1, and that's because B comma A is not an element of R1. Notice that A comma B is, but B comma A is not. And so that's just an example of how this notation might work. But there's also a really nice way to look at these things via a visual representation. So what you do is you think about every element of your set as being a vertex of a graph or a point in the plane. So let's do an example right here. Let's say this is our point A, this is our point B, and over here is our point C. And then if something is related to something else, then that gives us an arrow from the starting position to the ending position. So let's just talk our way through it. So this fact that A comma A is in R1, in other words, A is related to itself, says that there's a loop from A back to itself. So this loop is playing the role of this A comma A here. And then what about A comma B? So A comma B would be an arrow from A to B. So an arrow from A to B, so something like that. So that arrow from A to B, just to reiterate, that's like from this ordered pair here. So the left term in the ordered pair is the initial point of the arrow, and the right term in the ordered pair is the terminal point of the arrow. Now let's notice that B comma A is not in R1. That means there's no arrow going back from B to A. So there's just a one direction arrow. Okay, so now let's look at A comma C and C comma A. So A comma C will be a path from A to C like that, and then C comma A will be a path back from C to A. So this would be a picture of R1. So maybe we would put R1 over here to say that that's a picture of R1. Okay, so while we're at it, let's maybe make a picture of R2 as well. So R2, so I'll still need my points A, B, and C, But this one has less arrows because there are less elements. Notice that each element in the relation corresponds to an arrow between points in this graph. So we have A comma B, so that gives us an arrow from A to B. We have B comma C, that gives us an arrow from B to C. And then we have C comma A, that gives us an arrow back from C to A. And that's all we have. We don't have any reversals of these arrows. And we also don't have any loops like we did right here. So let's maybe put a box around this. Now notice that since R1 and R2 are simply subsets of A cross A, that means we can take their union and intersection, and that will also give a subset of A cross A. So R1 union R2 and R1 intersect R2 will also be relations. So let's look at each of those. Maybe let's look at R1 intersect R2 first. So which elements do these have in common? Well, we have A comma B, and we also have C comma A, and that's it. So those are the only elements in common. So if we were to draw our picture again, so again, label these A, B, C, then we would have an arrow from A to B, like this. And then we would have an arrow from C to A, and that's all we would have for R1 intersect R2. And then I'll let you look at R1 union R2, but what you'll get is just exactly this graph right here for R1 with the inclusion of an edge between B and C, like this. Okay, so let's do some more examples. So this whole notion of a relation is really just an abstraction of things that we've seen before that we actually called relations between numbers. And so often we'll like to go back to previously known relations that we've seen in other classes in order to further motivate this study. So in fact, we could just take our relation to be the relation less than, and that's what we'll do in this example. So let's say we've got a set A, which is the set containing 1, 2, 3, 4, and we say that X is related to Y if and only if X is less than Y. So let's start by writing this relation down as a set of points. So let's notice that 1 is related to 2, so that means we have 1 comma 2 in this set. That's because 1 is less than 2. And then we also have 1 being related to 3 and 1 being related to 4. Again, because 1 is less than 3 and 1 is less than 4. Next, we have 2 is related to 3 and 2 is related to 4, and finally 3 is related to 4. And that would be all of the entries from this set R. Okay, so now let's maybe make a picture of this. So I'll just put my numbers in a string. So let's say 1 is here, let's say 2 is here, let's say 3 is here, and maybe let's say 4 is here. So we need an arrow from 1 to 2. We also need an arrow from 1 to 3, and finally we need an arrow from 1 to 4. And that's because 1 is smaller than 2, 3, and 4. And then we need an arrow from 2 to 3, and we need an arrow from 2 to 4. And that's because 2 is smaller than 3 and 4. And then finally, we need an arrow from 3 to 4. And that would finish off our picture. Okay, so now we're gonna look at one more set of examples before we look at some characteristics that relations can have. Now let's look at two related relations. So let's say R sub 1 is the set of all points x comma x squared where x is a real number. Let's notice that this is naturally a subset of R cross R. That means it is a relation on the set of real numbers R. Okay, so let's maybe graph this one first to get started. So notice that this is exactly the graph of our favorite parabola y equals x squared. That's because x is like a free variable, but then the y variable depends on x. So let's color code this. Let's say here we will graph this relation in yellow. So that means we simply need the graph of a parabola. So we need something like that. Great. And then let's look at our second relation, which I'm actually going to change for no reason then it makes a nicer picture. And so this is going to be the set of all points x comma y in R2, where y is bigger than x squared. Let's also notice that this is a relation on R cross R. Great, which means we can graph it the same way. But what's that? That's the set of all points that lie above this parabola. So let's maybe color code this in blue. So if we were to graph all of these points, we would graph every y value which is above its corresponding x value on the parabola. So we would graph everything inside the parabola. And notice we do not graph the parabola itself. I think that's a good variety of basic relations. Now let's look at some properties that relations can have. So there are three very important properties that a relation might have. And if it has all three of those properties, it's super special. And it's the type of relation that we'll talk about next time. So let's suppose we have a relation, we'll call it R. So let's just recall again that that just means that it's a subset of A cross A. Then we say R is reflexive if for all x in A, x is related to itself. So if you're talking about a relation, it often kind of makes sense for something to be related to itself. Then we say R is symmetric if when x is related to y, we know that y is related to x. But we can put this symbolically into the conditional x related to y implies y related to x. So that's how we would prove this type of thing. And then finally, we say R is transitive if when x is related to y and y is related to z, we know that x is related to z. So again, you could put that into a conditional with an and statement now. So x related to y and y related to z implies x is related to z. Okay, so let's look at a chart of standard relations on the integers, and we'll prove some things about some of these relations and then just argue the properties of the rest. So I have the properties here: reflexive, symmetric, transitive. And then I've got my relations: less than or equal to, divides, does not divide, and is not equal to. So I don't have greater than or equal to, because that's really just a reflected version of less than or equal to. So let's start with the less than relation. So maybe I'll put down here, we're going to start looking at the less than relation. So let's notice it is not reflexive. And we can see that via example. So 2 is not less than 2. 2 is equal to 2. It's not strictly less than 2. So maybe we would say here, no, it is not reflexive. Is it symmetric? No, it's not symmetric. And we can check that it's not symmetric by noticing that 2 is most definitely less than 3, but 3 is not less than 2. So again, it is not symmetric, but it is transitive. So let's note that if L is less than M and M is less than N, then L is less than N. So that would be the transitivity property for less than. So I'll go over here and I'll put yes, it is transitive. Now, it looks like we didn't prove anything here, and in fact, we didn't. And that's because in order to really check this thing about less than, you need something about the integers at a more base level, but we're not going that deep here. Okay, now what about less than or equal to? So notice that it's not symmetric, so let's start with that. It is not symmetric. That's because 2 is most definitely less than or equal to 3, but 3 is not less than or equal to 2. But it is reflexive. That's because any number is less than or equal to itself, because we allow that equality. And then it's also transitive, so I'll put a yes here for transitive for the same sort of reason as this down here. Now, and then maybe we would finish this off by saying that m is less than or equal to m for all integers m. That's because m is in fact equal to m. So there's not really anything going on there. Okay, now what about equality? Well, I remember learning in grade school that equality was reflexive, symmetric, and transitive, and we even use those words. So perhaps you've seen that before, but that's really one of the defining properties of equality. So I'll just put yes for all of these. And now let's move on to divisibility. So looking at divisibility, is it reflexive? Yes, it is reflexive. That's because for all integers n, we can write n as 1 times n, but writing it as something times n means n divides n. So notice to prove that it's reflexive, we had to prove this universal statement. We had to do something. Whereas to prove that it is not symmetric, which we're about to do, all we have to do is give a counterexample. So that's important to notice. Okay, so we can go over here and put yes, it is reflexive. And shortly, that's just because everything divides itself. But it is not symmetric. And that's because, for example, 2 divides 4. So 2 most definitely divides 4 because 4 is 2 times 2. But 4 does not divide 2. But in order for it to be symmetric, 4 would have to divide 2. So anyway, that's our counterexample for symmetry. So it is not symmetric, but it is transitive. And I think that was maybe a homework exercise, but let's work through it just in case. So let's suppose that x divides y and y divides z, just to put it in this language over here. So let's notice that means that y is equal to a times x and z is equal to b times y for some integers a and b. So I'll just put down here where a and b are some integers. But now we'll take this version of y and plug it into y in this next equation. So let's see what that leaves us with. We'll have z is equal to b times ax. In other words, it's equal to ab times x. But that means z is a multiple of x, but having z be a multiple of x means that x divides z. But that's exactly where we needed to end to show that this is transitive. So I'll put yes, this is transitive. Now what about the relation does not divide? Well, in fact, that's neither reflexive, symmetric, or transitive. And I'll let you check that one on your own. But that's essentially because if you negate does not divide, you get does divide. Okay, so now let's move on to inequality. Okay, so looking at inequality, it is not reflexive. And we can see that because 3 is equal to itself. It's not equal to itself. So anyway, that's an example of it not being reflexive. But you could say that every number is equal to itself, but that means that every number is not equal to itself. So anyway, it's pretty clear that this is not reflexive. But is it symmetric? It is symmetric because note, if x is not equal to y, then y is most definitely not equal to x. So that shows that it's symmetric. So we have yes, it is symmetric. Now, is it transitive? Well, in fact, it is not transitive, and we can do that via an example as well. So let's note that 2 is most definitely not equal to 3, and 3 is most definitely not equal to 2, but 2 is equal to 2. But for it to be transitive, we would need 2 to not be equal to 2. So anyway, that's a counterexample for it being transitive, so it is not transitive. So there's our filled in chart. We didn't do everything, but I urge you to do the rest on your own. So separately, we talked about graph visualizations of relations, and we also talked about these properties. Now I'd like to put those together to show some visual cues that a relation is reflexive, symmetric, or transitive given its graph. So it's reflexive if every point has a loop. So if you look at your graph of your relation, then you look at a point and that point should have a loop kind of around it. So where the terminal point and the initial point of that arrow is that point. Okay, so that's a hallmark of reflexivity is every point has a loop. So what about symmetry? Well, so symmetry says that every arrow has an arrow back. So here we need 2 points. And let's say we've got 2 points and we've got an arrow from one to the other like this. So at the moment it is not symmetric, but if it were symmetric, we would also have a path backwards. So it's like having a two-way street instead of having a one-way street. And then what about transitivity? I like to think about transitivity as having a shortcut. So I'll just say there is always a shortcut for 2 connected arrows. So there are 2 cases of this to be interested in. So let's say we've got 3 points like this. let's say we have an arrow from this top left point to this bottom point, and then another arrow like that. So let's say that's what we start with. So transitivity will tell us that there's a shortcut. So in other words, there's an arrow simply from this point to this point. And then there's one other way to think about transitivity, and that involves only 2 points. So say we've got 2 points like this, and we have an arrow from one of them to the other one and back again. But now if we apply transitivity to this scenario, it will create a loop at either end. So that's important to notice as well. Okay, so now let's do some examples of checking these conditions. So now we're going to show that the relation on the integers given by congruence mod n is reflexive, symmetric, and transitive. Okay, so let's do these one at a time. So we'll start with reflexive. Great, and so let's look over here. In order to show it's reflexive, we need to take an arbitrary integer and show that it's related to itself. So let's do that. So let's suppose we have an arbitrary integer, which I'll maybe call a, and observe that 0 times n is the same thing as a minus a. Well, that's because a minus a is 0, but 0 is the same thing as 0 times n. But notice that implies that n divides a minus a. So there's nothing really fancy going on here. But notice that implies that a is congruent to a mod n by the definition of congruence mod n. But then since we started with an arbitrary a and showed that it was congruent to itself, then we have indeed showed that this is reflexive. Now let's show that it is symmetric. So that means we need to take two things that are congruent mod n and show that we can reverse their order. So let's suppose that a and b are in Z such that a is congruent to b mod n. And where we'd like to end up with is b is congruent to a mod n. So let's see how we can get there. Notice by definition of congruence mod n, that means n divides a minus b. But that means a minus b is equal to n times k for some integer k. But now we can just take this equation and multiply it by minus 1. That will tell us that b minus a is equal to n times minus k. But since k is an integer, minus k is also an integer. So this equation tells us that n divides b minus a. But n dividing b minus a is exactly the condition that we want to end this off, which says that b is congruent to a mod n. So that's good. We have symmetry now at this point. Notice we took arbitrary a and b satisfying a congruent to b mod n, and we ended up with b congruent to a mod n, but that's exactly what we needed to do. Okay, good. So now let's work on transitivity. Okay, so for transitivity, we need to start with three things that are related in this sort of scenario. Maybe we'll use A, B, and C here. So we need A to be related to B and B related to C, and then we need to show that A is related to C. But remember, our relation here is congruence mod n. So let's suppose we have A, B, and C, which are integers, such that A is congruent to B mod n, and B is congruent to C modulo n. Okay, but then definition of congruence mod n will tell us that n divides a minus b and n divides b minus c. But then definition of divisibility says that a minus b is equal to n, maybe I'll call it times x, and b minus c is equal to n times y, and this is for integers x and y. So just to reiterate, that's by the definition of divisibility. But let's recall where we're trying to get. We're trying to get to a is congruent to c mod n, so we need something like a minus c. So how can we do that? Well, let's take these two equations and add them. Notice if we add these two equations, that gives us a minus c is equal to n times x plus y. But that equation tells us that n divides a minus c, but that's exactly the condition for a to be congruent to c mod n. So let's make sure we've done the right thing. We assumed that A was congruent to B mod n, and B was congruent to C mod n, and then we did some calculation and we ended up with A is congruent to C mod n. But that's exactly what we need for transitivity. Okay, let's look at another. So our next relation will be on the integers as well. And let's say in this case that A is related to B if the absolute value of A minus B is less than or equal to 3. And then our goal is to show that R is reflexive and symmetric, but not transitive. Okay, so let's do this one at a time, just like we did before, starting with reflexivity. So reflexivity is really simple in this case. Let's notice that for all, maybe I'll call it A, which is an integer, the absolute value of A minus A is equal to 0, but 0 is most definitely less than or equal to 3. So that means that in fact, A is related to itself. And since A was chosen arbitrarily, that does it for this reflexivity. Okay, so now let's check symmetry. So let's suppose that A and B are integers such that A is related to B. But notice, putting it in terms of the definition of our relation, that means the absolute value of A minus B is less than or equal to 3. But we want B to be related to A, which would be the absolute value of B minus A. So let's note that the absolute value of B minus A is the same thing as the absolute value of -1 times A minus B, but the absolute value will cancel that -1 out, just leaving us with the absolute value of A minus B, which is most definitely less than or equal to 3 by our given. So that tells us that yes, B is related to A. So it is symmetric. So now let's move on to transitivity, and we'll show that it is not transitive. And we can find a pretty simple example of this. Notice that 6 is related to 3. That's because 6 minus 3 is equal to 3. That's less than or equal to 3. And 3 is related to 0 because 3 minus 0 is equal to 3, which is less than or equal to 3. But 6 is not related to 0. And that's because the absolute value of 6 minus 0 is equal to 6, which is strictly greater than 3. So here, this is reflexive, symmetric, but not transitive. Okay, let's do one more. So for this example, we'll consider a relation on the real numbers defined as follows. So x is related to y if and only if x squared plus y squared equals 1. Now let's check these properties. So starting with the reflexivity. Maybe before we start to check these properties, let's notice that all of the points that satisfy this rule lie on this circle of radius 1. So this is not reflexive. So here we'll say, no, it is not reflexive. And why is that? That's because 1 is not related to itself. And we can see that 1 is not related to itself because 1 squared plus 1 squared is equal to, let's see, the number 2, which is not equal to 1. Okay, is it symmetric? Well, yes, it is in fact symmetric, and we can prove this. So let's suppose that I'll call them A and B. So A is related to B. So that means that A squared plus B squared equals 1. But then that means that B squared plus A squared equals 1 by the commutativity of addition. But that means that B is related to A. So it's quite simple to prove that this thing is symmetric. Now, is it transitive? Well, in fact, it is not transitive. And actually, if you have something that's always symmetric, but never reflexive, you can automatically know that it's not transitive because you'll never get those loops that we talked about with that picture before. But anyway, let's show that it's not transitive by an example. So let's note that 1 is most definitely related to 0. That's because 1 squared plus 0 squared equals 1. And 0 is related to 1 for the same reason, because 0 squared plus 1 squared is 1. But 1 is not related to itself by our previous calculation. So this is a counterexample for transitivity. So we're going to end by extending this definition of a relation to two different sets, but we're not really going to do much with that. And then we'll have some warm-up exercises. So now we want to look at this very, very slight extension of our notion of a relation, but we won't do much with this. We'll just pick up on it later when we talk about functions. So there's a little bit of a spoiler. So a relation from a set A to a set B is simply a subset of A cross B. But now notice if we're in two different sets here, A and B, the notions of reflexivity, symmetry, and transitivity don't make any sense. Notice that A comma A doesn't make any sense because every element of A may not be in B. That sort of helps us figure out why symmetry and transitivity may also not make any sense, because these could be wildly different sets. Okay, so let's look at a couple of examples. So let's say we've got a set A, which is 1, 2, 3, and our set B is A, B, C, D. So these are different sets. One is made of numbers and one is made of letters. And then let's say we've got a relation between these sets of 1 comma A, 1 comma B, and 2 comma C. So this is a fine relation. You might light up and think, hey, this is not a function, but we're not there yet. We're not thinking about this type of stuff yet. This is a relation. And we could maybe make a picture of this relation as follows. Let's put A and B each in a line. So here we have 1, 2, 3, and here we have A, B, C, D. And then we could do our arrows for the things that are related. So 1 is related to A, so we've got an arrow from 1 to A. 1 is related to B, so we've got an arrow from 1 to B. And then 2 is related to C, so we have an arrow from 2 to C. And then that would be the whole picture of this. So let's look at another one, which is a little bit more interesting. Let's say we have our relation. It's a subset of Z cross the set containing 0, 1, and 2. And we say that A is related to B if and only if A is congruent to B mod 3. So I guess implicitly built into this is everything is related to either 0, 1, or 2 mod 3, but that's not too hard to show with the division algorithm. So maybe we could make a picture of this as well. So let's lay out all of the integers at the top. So 0, 1, 2, 3, 4, 5, 6. Then let's maybe go backwards, -1, -2, -3. Maybe that's enough integers. And then we'll have down at the bottom 0, 1, and 2. And then we'll put arrows if they're congruent mod 3. So notice -3 is congruent to 0 mod 3 because it's a multiple of 3. 0 is congruent to 0 mod 3, and 3 is also congruent to 0 mod 3, as well as 6 being congruent to 0 mod 3. So -3, 0, 3, and 6 all collapse down to 0. But then notice that 2 collapses to 1, 1 collapses to 1, and 4 also collapses to 1 mod 6. That's because they're all 1 more than a multiple of 3. And then we've got one more thing. So what about -1? Well, -1 is 2 mod 3. It's 2 more than a multiple of 3. 2 is 2 mod 3, and 5 is 2 mod 3. So that would be our picture in this case. So it's a little bit messy. But that being said, I think we kind of get an idea of what's going on. Okay, so now I'm going to give you some warm-ups. So here's some nice warm-up exercises based on what we just saw. So let's consider the relation less than or equal to on the set 0, 1, 2, 3. So let's illustrate it with a graph and prove whether or not it is reflexive, symmetric, and or transitive. So next, let's consider the relation with the following graph. And then your goal is to translate this graph into a relation with sets. So what would the set A be? And then what would the set R, which is the subset of A cross A, be? Then, given a finite set A, how many relations are on A? So this may seem like difficult and tricky, but just go back to what you know about exactly what a relation is, and it shouldn't be too bad. And then finally, let's consider the set R, which is all ordered pairs of real numbers x, y, such that their difference is an integer. Now, your goal is to show that this is reflexive, symmetric, and transitive. And that's a good place to stop.